In our previous modules, we have discussed about several new concepts of rationality. In particular, we have discussed that dominance cannot explain all reasonable outcomes, because there could be some games where there isn't any dominant strategy or dominant strategy equilibrium. Then we relax the idea of dominance into what we defined as the pure strategy Nash equilibrium, which is based on unilateral deviations. And in some sense, this is the notion of stability. If you ever end up in a pure strategy Nash equilibrium, you should not be deviating from it, because that's not going to give you any better payoff. On the other hand, we have also defined something like a rationality for a risk-averse agent or player. That notion was max-min strategies, which in some sense is giving you some security. That is, even if all the other players are behaving as badly against you as they can be, still you can guarantee at least the max-min max-min value out of your utilities. So when we are discussing these two notions, it's a very natural question to ask: what happens when you do the iterated elimination of dominated strategy? So remember that when we were trying to discuss about what happens in a game when people are rational and therefore they remove their dominated strategies, we should also ask what happens to this new notions of equilibrium. Does it create new equilibrium? Does it eliminate reasonable equilibrium? Now this is the old example, a slightly modified one. Whenever you are eliminating the strategies of all these players in a certain order, you get a specific outcome. In a different order, you get a different outcome. Now the question is, does it change the max-min value? Let us first discuss about the max-min value. So in the above example, if you look at the max-min values of player 1 and 2, so max-min for player 1 is nothing but you pick the row minimum. So for player 1, you take the minimum among this, which is 0. Similarly here, if you take it, is 2, and here also it is 0. So the max of all those means is essentially 2. So the max mean value for player 1 is going to be 2. Similarly, you can find that for player 2 it is 0. Now suppose for player 1, B is a dominated strategy, weakly dominated strategy. So if you remove that, you can see that the max mean value, recompute the thing again, you will find that player 1 still has the max mean value to be 2, while the max mean value for player 2 has increased to 1. So is it just a stray observation? The question is, the answer is no. It is actually true that max mean value is not affected for the players whose dominated strategy is removed. So for instance, in this case, player 1's dominated strategy was removed, so therefore his max mean value did not change, while player 2 had a change in his max mean value. So let's state this formally and also prove it in this result. So consider a normal form game, and we represent a game with a set of players, a set of strategies for each player, and the utilities. And suppose this SJ hat is a dominated strategy for player J. And now you can remove that strategy from player J's strategy set, and the residual game that you get is denoted by G hat. Now the max mean values, the theorem claims that the max mean value of J hat for J in G hat is equal to the max mean value of the same player in G. So the intuition is the following. So this is essentially formally stating the previous result. When you are trying to find the max mean, it is actually the maximum of all the minima, right? So elimination, so when you are eliminating the dominated strategy, the only way the max mean can change is if you are removing the row that gives you the max. And that cannot happen. That cannot be a dominated strategy. That is the whole intuition. So first, let us write down what is the max mean value of J in the original game, so in G. So this is by definition. And similarly for G hat, now you have a change in the strategy set. You don't have this SJ hat anymore. The rest of the things remains the same. So we'll have to show that these two things are essentially same. Now, because SJ hat is a dominated strategy, so then there must exist some TJ which is not equal to SJ hat, and therefore TJ also remains in the residual game. This inequality must hold. So yeah, so it does not necessarily mean whether it is a weakly or strictly dominated. For both it works, and this inequality should hold for all S minus J belonging to capital S minus J. Now what you can write is, if you look at the minima, so let's say the minima that you get when you consider this expression, player J is picking the strategy T of J, and all the other players are picking the strategy S minus J, and you are taking the minima over it. Let's call that minimizing strategy the strategy of all the other players except J to be S tilde minus J. So this one is going to be greater than or equal to Uj of Sj hat S minus J tilde. This is just coming from this previous conclusion or the fact. Because Tj is dominating Sj hat, it should do for every S minus J, including S minus J tilde. Now, this last part of the inequality is again by the definition of minima. So if you just pick one strategy for all the players except J, then if you look at the minima of that, of course that is going to be smaller. Now, all that we find out from here is, if you take the maxima of this expression, and the maxima is taken with respect to all the strategies which remains in the residual game. So these are the strategies that you have in the residual game. It does not it is not including Sj hat. Then the max that you will get is of course going to be greater than or equal to the minima. So this right hand side here. So of course you are taking the maxima over all the strategies. It must be greater than the one specific strategy, which is Tj. And now we also know that this inequality also holds here. This is just coming from the previous inequality. So good, we actually have two things: the max mean over the so this is essentially the max mean value except agent I, right? So except agent J. So if you look at this is exactly the same value. So you can call that this is Vj hat, the max mean value of J in the residual game. Now what you do is essentially the Vj, the max mean value of the for J in the original game G. Now that is going to be the max mean over the whole set. So there it also includes Sj hat, which has been eliminated because that is a dominated strategy, and for the rest of the sets. Now you can split this into these two parts. So in one part we are just going to write the same max mean, but except the strategy Sj hat, and for the other part we are just writing Sj hat, right? We can always write this, and we pick the max of both these two things, and that is going to be the max mean of the original game. Now what we have just mentioned, what we have just shown is that this value here is actually greater than or equal to the other value. So go back here, we have just shown that this value is essentially larger than that value, right? So even if you eliminate that dominated strategy, its contribution in the original max mean is not going to be counted, because what you have is essentially the Vj hat, right? So this actually comes out as the outcome of this max, and that is essentially the Vj hat. max min value of the reduced gain. So we are done. So we wanted to show that the max min value of Vj and Vj hat lower bar both are same, and that's what we have proved.